Okay, yeah. So first of all, thank you for the opportunity to present during this second Yushan Conference. I appreciate it with all you good people in the audience. So I'm going to present to you a paper we've been working on, which we have called Bankruptcy Prediction of Privately Held SMEs, a study of input variables using feature selection methods. So as in the introduction, my name is Ranik Wahlström. I'm from the Norwegian University of Science and Technology. And this paper is in cooperation with Professor Florentina Paraskiv, who also is from the Norwegian University of Science and Technology, as well as the University of St. Gallen. She was the one raising the questions in the end of the last presentation, so she is also here today. And it's also in cooperation with Professor Marco Schmidt from the University of St. Gallen. So models for company bankruptcy prediction are important for many actors, and among them are banks and regulators. So banks use such models, among other things, for making credit decisions and setting the interest rates offered to potential borrowers. Regulators, on the other hand, use such models for, among other things, stress testing the current state of the financial markets, but also when they do on-site supervisions of banks. So the choice of input variables for such bankruptcy models are often ad hoc, and it's also heavily debated among both academics and practitioners. So to cope with this, to fill this gap, we in this study use alternative feature selection methods to derive the input variables. and by doing so, we apply the data itself and let them guide us. The data for our analysis are annual financial statements of privately held Norwegian SMEs from 2006 to 2014. And the reason why we've chosen privately held companies and SMEs are because such companies are heavily underrepresented in the existing literature. Indeed, the existing literature on bankruptcy prediction tend to focus on larger companies and listed companies. In addition, such companies are also a significant proportion of the bank's loan portfolio, and they make up a large proportion of the economy. So from all these financial statements, we derive 155 different accounting-based input variables, all identified in the existing literature. So after doing this, deriving these 155 accounting-based input variables from all these financial statements, we apply feature selection methods to select the most appropriate input variables. And in particular, we use one feature selection method within each group of feature selection methods there are. So first of all, we use one filter method, and in particular, we use a filter method with the Pearson correlation coefficient as the criterion. We also use a wrapper method, and for the wrapper method, we have chosen the IFRS algorithm. And then we finally use an embedded method. And for the embedded method, we have chosen the lasso method. We have also made our results with the ridge regression and different elastic nets, but we found in all cases lasso to outperform the others, so that's why we focus on lasso in our paper. After the feature selection methods,
sorry, what means embedded, Ranik? Embedded, what does embedded mean?
Embedded methods are methods that do feature selections as part of the training process. Mm-hmm. So they use shrinking methods in the optimization problem.
Or they add you have all the 155 accounting variables for your 8 years available?
Could you repeat if I have?
All your 155
yes.
Variables, right? For your accounting variables. You have them available for all the 8 years?
Yes,
for all
yes.
the 8 years? Okay.
Yes, I have available all the financial statements as they are reported to the Norwegian authorities, and there they have detailed numbers for all accounting. So I know in Orbis database, for example, there are a lot of missing values for many accounting numbers, but in this data set, there are no missing values. It's the same numbers which the tax authorities use, so no missing.
Thank you. Thank you.
Yes, thank you for the questions. Please let them come during my presentation. So after these feature selection methods have selected the input variables, we use them in models developed using 2 different tools. And we chose one tool within each of these, let's see, groups of tools, which some previous studies have mentioned. I'm not sure about these groups, but anyway, we use one logistic regression. We use as one method a logistic regression, which is called a statistical method, very interpretable and logical, but not so flexible. And then we use an artificial neural network, which many tend to call artificial intelligence method for bankruptcy prediction. When we do predicting, we do so in a 1-year perspective. And this is because it's the most common use prediction horizon among both practitioners and academics. Right, you typically have the annual financial statements each year, and then you predict the bankruptcy before the next financial statements come. It's also it is in accordance with the Basel III regulatory framework. So that's what we chose in this horizon. So the procedure in our analysis looked like this. It's a 6-fold cross-validation where we account for the time dimension by using a rolling window. So in particular, for each fold, we use 3 accounting years. In the first fold, we use the accounting years 2006, 7, and 8, and take all the financial statements from these accounting years and use them for first selecting the input variables using the feature selection methods, and then training the models with the tools we presented. And finally, we do the auto-sample performance on all financial statements on the following accounting years. So for the first fold, it's all the financial statements in 2009, and so on for all the 6 folds. So this is our first results. Here we see the auto-sample AUC for different input variable sets when we use the logistic regression as tool.
One more question.
Yes, please.
I saw bankrupt, non-bankrupt, right? Mm-hmm. So you did something like augmenting the bankrupt actually, because there were not so many bankrupts, right? So because they had the same number, right? Or
yes, we do a matching. And we do we use an oversampling technique to.
I know. I have papers on that.
I know you do. I even cite some of yours. So yeah.
Yeah, thank you.
Also in this paper, actually, from 2009.
Which year? It's which year? Yeah, that's right.
Yeah, exactly, it was smoothing support vector machines.
His PhD student is just sitting in the next door, right? She will enjoy
it. Oh, really?
Yeah. Very nice there.
Very good.
The world is small. The world is very small.
Yes, it is indeed. So,
fortunately.
Thank you for the good questions, Professor Herle. So, did I answer your questions?
Yeah, of course. I wanted to hear the word oversampling.
Okay, good. Well, thank you. So, on this graph, we show the results when we use logistic regression, but we see the same kind of patterns, almost exactly the same, when instead using an artificial neural network. So this what we find here is robust across both these tools. So AUC stands for the area under the receiver operator characteristic curves, which in practice has a value between 0.5 and 1, where the higher value is better. The horizontal axis here shows the number of input variables in this set. So first of all, I will present the 5 benchmark input variable sets we have chosen, and these are shown on the table on the right. So we have chosen to use some input variables from some popular models in the existing literature, namely the input variables used in the Altman model of 1968, also the input variables from the Altman and Sabato model, the Taffer model, and the Smijewski model. In addition, we have used the input variables used in the Zebra model, and the Zebra model is the bankruptcy prediction model used by the Central Bank of Norway and developed by the Central Bank of Norway, and also being used currently by the financial regulatory authorities in Norway. So, and we've chosen this one because we, after all, use Norwegian data, so it's interesting to see how we perform against this one. And I should also note that all of these models are, of course, using other tools and developed for other market and other times. So we only derive the input variables from these models, not the models themselves. Okay, so these are given in dots in this plot. So for example, here you see the performance of the input variables of the Altman model, whereas the AUC is about 0.77. And we also see that it's here on the horizontal axis, meaning that there's 5 input variables in this input variable set. For the feature selection methods, we have drawn them as lines, and this is because we can predefine the number of input variables the feature selection methods should select when they are being used. So these can have any type of number of input variables which we pre-select. So for example, the lasso method has this performance when 1 input variable is selected, then 2, 3, and so on. We also see a red line here, which is the performance of input variables it's a performance when using input variables randomly selected. So comparing against this red line, we first of all see that it's important to carefully select the input variables. You shouldn't just randomly select something from your financial statements. We also see that the best performance is achieved with the lasso and the wrapper feature selection methods. And among the benchmark, we see that the zebra model is close behind, which is as expected since it's after all developed for the same type of data as we use. So this is the auto-sample performance, the prediction power, if you like, of the input variable sets. What's also important to consider when using feature selection methods is their stability. In other words, their ability to select approximately the same input variables when presented to different subsets of the data. So we also look into this, and this is the results. Here we see the graph with the same on the horizontal axis, namely the number of input variables in the set. And on the vertical axis here, we see the number of unique input variables selected across these 6 different folds we presented earlier. So for example, yeah, so the red horizontal line here shows the worst possible cases. In other words, when the feature selection methods selects completely different input variables each time for each fold. The green diagonal line, on the other hand, shows the best possible cases where the feature selection methods select exactly the same input variables for each fold of data. And here we see that the filter and lasso method are closest to the green horizontal line, meaning that they are most stable. And we see that the lasso method is slightly more stable than the filter method. So when considering the auto-sample performance, the predicting power from the previous slide and the stability from this one, we see that overall the lasso method is the one performing the better. And given the marginal increase on AUC from previous slide, in other words, we see that the AUC is increasing with the number of input variables, but only up to a certain point when these lines are flattening out. Based on this, we choose to let the lasso method select 10 input variables in the set, and then we dive into and look closer into the input variables selected for this predefined number of input variables. And if we let the lasso method select 10 input variables for each of the folds, it ends up with 12 unique input variables across all folds, and these are those 12. And as we can see, no time for details on them, but as we can see, they are selected among many categories of input variables, and most importantly, the input variables represent 4 of the main aspects of a company's financial profile, namely liquidity, profitability, leverage, and solvency. However, none is selected among the main aspect activity, but this is also in accordance with the revision of the Altman 1968 model, which was done in the 90s, which concluded that the input variable measuring activity should indeed be excluded because it was very insignificant, but also very industry sensitive. Finally, we also see some similarities or several similarities with the zebra model, which is as expected. Here we see the selected input variables when used in a logistic regression framework. So for each fold here, we see the fold for 2009, 2010, and so on. For each fold, we see a coefficient associated with 10 of the input variables, as well as an intercept coefficient. And what we see with the coefficient values are that all signs are as expected. And we also find that the coefficient values are very stable across all these folds. We have also derived Z-scores using Wald statistics, which is shown in the parentheses here, and we find that all coefficients are very significant. When we look at the in-sample fit, we see, which is here measured by AUC, Breer score, AK information criterion, and pseudo R-square. We find that these measures show a very good and stable in-sample fit. And we also see the same when we look at the out-of-sample performance, here measured by AUC, Breer score, and decile rankings. It's also very good and very stable across time. So far, so good. So we have looked at these methods and models and coefficients when using statistical measures. But what does this mean for practitioners? A model is slightly better in AUC. What does it mean for a practitioner? How many more profit can I make when using this model having a slightly better AUC compared to this other one? Well, AUC, the statistical measures, and also all other statistical measures, R-square and so on, have certain drawbacks which are not captured when models are used in the real world. And one particular challenging thing with the statistical measures when evaluating bankruptcy prediction models are that these metrics assume equal costs of different types of prediction errors. So in our case, or when you're doing bankruptcy prediction, for example, if you're a bank, you have two types of errors. The first error is the failure to correctly predict a company's bankruptcy. And in this case, you lose a large portion of any granted loans. The other type of...
You have 4 more minutes left.
Okay, yeah. Then I will, thank you. Okay, so the other kind of error which one can do is to overestimate the probability of bankruptcy of good customers. In this case, you maybe offer them too high credit spreads and they instead mitigate towards offers from other banks. In other words, you lose on the incomes from these good customers. So clearly, these types of error represent different types of cost, but these statistical measures assume that they are equal. So because of this, we propose to alternatively simulate a credit market to evaluate the bank profitability under different modeling choices. So for doing this, we use the effective size of the whole Norwegian SME loan market by deriving the amount each company wants to borrow from their financial statements. And then in this simulated credit market, we let there be 8 banks. 3 of these 8 banks are using the input variables selected by the feature selection methods, respectively, while the 5 others are using the input variables from these benchmark subsets. And from these input variables are used in a logistic regression framework to calculate the probability of bankruptcy for each borrower. And based on this, the 8 banks perform credit decision for each potential borrower, as well as credit pricing. In other words, offering an interest rate based on these probabilities. So all details are in the paper, but through this, we can make the profits of each of these 8 banks. And clearly we see that the profits of the bank using the lasso method for input variables is doing much better than the others. Also, when accounting for risk by dividing by the total amount lent and also the risk-weighted amount lent, which is shown in the paper, we see that the lasso method is doing better. Here we see the return on assets of the bank using the lasso method is slightly above 6 and very stable. We see that for some years the filter method is doing slightly better, but this method nevertheless yields so small loan portfolio that it's not directly compatible with the lasso method. And so this is an example on that small differences in AUC, for example, between the wrapper method and lasso method, which you saw on the previous slide. Small differences in this statistical measure AUC nevertheless means a large difference when used in a simulation, simulating the real world for a bank, for a bank's perspective. And the reason why this happened is because what we see here we see on the left-hand side, we see the average credit spreads offered by the different banks to the good customers, in other words, those who do not bankrupt. And on the right-hand side, we see the average credit spread offered by these 8 banks to the bankrupting customers, in other words, the bad customers. So here we see that the offered credit spreads to these good ones are slightly better when for the bank using the lasso method compared to the bank using wrapper method. Thus, the bank using the lasso method captures more of these good customers and make much profit. but they do not end up lending more money to bad ones compared to the wrapper method. So these two sides effects affect the profitability. So just conclusions, we recommend that if you use a bankruptcy prediction model, if you're a bank regulator or other, you should carefully choose your input variables based on the market you're operating in, not just use anything which have turned out to be good in the past for models developed in the 60s, 70s and so on, but use data-driven feature selection methods to let the data itself guide you on what input variables are most appropriate. We have also seen that the best performance is achieved when using the lasso method, and we have also simulated economy to look at the effects out in the real world for banks, and we again confirm the superiority of lasso method for selecting input variables. We are also given insights in input variables for privately held SMEs, and for this particular market we have used in our study, we offer an improved bankruptcy prediction model to the benchmark, which is currently used by the financial regulatory authorities in Norway, as well as the Central Bank of Norway. So that's all from me. Thank you very much, and I'm looking forward for questions if there are any.
Thank you, Ranik. Are there any questions from the audience?
Yes, many.
Good. Oh.
Okay, so what is the LHS of your lasso actually? LHS means left-hand side. Is it the probit, the logit? What is it really? What is your predictor variable in your lasso? That is a little bit washed out in the brain when I followed your talk.
Yes, it's the bankruptcy itself. So the left-hand side, yeah.
Why 0, 1?
0, 1, yes, correctly. Mm.
So you do a linear predictor for 0, 1 variable?
For the logistic regression, we use a log odds linear. That's correct.
Yeah, but logistic regression is nothing else than a smooth squash function or sigmoid function that operates on a score, a linear score. The same is true for the lasso.
Yes.
So that's why I'm asking what is on the LHS of the lasso. Why don't you use the log odds on the left-hand side? Then you would
yes. It's a log odds. So we're using the lasso in a logistic regression framework. Okay. So it's a logistic regression.
I understand.
Log likelihood. Okay. Yeah. Thank you.
Sorry that I'm a little bit academic here because I like this very much what you're saying here. Then you would call this a generalized linear model with feature selection, essentially, when you are talking about the log odds on LHS, right? And there has been a tendency 40, 50 years ago to say this microeconomic approach, call it probit or logit model, is bull BS, sorry. Why? Because it assumes a so-called linear utility, with random errors that are of logistic or of normal stochastic nature. Yes. And must get rid of that by so-called single index models. That means you non-parametrically estimate this function. Is this what your network does, or your network probably doesn't cough up like your score, right?
Yeah, exactly. So our artificial neural network is a feed-forward neural network, but we have made it such a way that there's no assumptions about neither the error terms or the data itself. So we use
That's why I call it always a useless approximation operator when I talk to banks, because they would like to know what are the marginal effects, right? So what happens if the bank does this and that on one of the 155 variables? Is it 1% going down? How much does it change the score, you could say, or the likeliness of going bankrupt?
Yeah, so for the logistic regression, we show that on this table you see, and of course with the coefficient. We could of course do a similar analysis on the ANN, for example, using not sharp ratios, but shape values, for example. We haven't done that analysis. We think the selection of tool is outside the scope of this study. We want to have focus on the feature selection method. and we made sure that our findings are robust across these two tools, which one have this all this assumption which you highlight, the logistic regression, but also one without so many assumptions, the ANN. But yeah, I agree that the way we presented it in here now gives only a black box presentation of the ANN. So
yeah, it's too much ML, where ML doesn't stand for maximum likelihood, but for machine learning. I understand that, yeah. So it's a perfect talk. I like it very much. And
but
please come to Berlin. I saw a flight from Copenhagen to Berlin today. So Copenhagen shouldn't be too far from Trondheim or wherever you are.
No, and it's very close if it hadn't been for this pandemic, but it will be over, and I will be glad to see you all in
come.
Berlin.
Yeah.
Thank you.
Together with Florentina. Thank you very much. Very nice talk. Thank you.